Rich is still outside. It's like, hello, everyone. Thank you for coming today. My name is Yanqing. I'm the organizer of this Tea Time Talk series. Before we start, there's two reminders. One is that we are live streaming on YouTube, and the second is that before you ask questions in the Q&A session, please wait until the mic is in your hands. Thank you. And today we have Kris the Asis, and the topic is important sampling weights in offline learning. Thank you.
All right, thank you everyone. My name is Kris, and I'm one of Rich's PhD students, and this is a talk titled Value-Aware Importance Weighting. And so this is in the context of off-policy learning, and so to give a quick overview of off-policy learning, you can imagine you have some penguin that's going about its day, it's making decisions according to some behavior policy mu, and at some point it might stop and think, like, what would have happened if I was sampling my actions from some other policy pi? And it might ask the same question about yet another different policy pi. And so that's one of the promises of off-policy learning, where from this one stream of experience sampled from its behavior, it could reason about many different target policies. And one way that we approach off-policy learning is through importance sampling. And this provides a strategy for reweighting updates under one distribution, in this case, the behavior policy, to look as if they were sampled under another distribution, the target policy. Now, importance sampling is well known in the literature to have really high variance, and so this can lead to a lot of instability in practice. And so this is a problem, and hopefully this work will make some progress in this direction. So to be a bit more formal, importance sampling is defined to be the ratio between two distributions, in this case, the target policy pi and the behavior policy mu for some state action pair at time t. And let's say you had some action values q, then we have that the expected value of rho times q when sampled under the behavior policy will give you the expected value of q under the target policy. And we also have that the expected value of rho is 1 when sampled under the behavior policy. So to clear up some of my notational shorthand, whenever I say like q of t, this is implicitly the action value of the state action pair at time t. And all of my expectations are implicitly conditioned on state. So to give a motivating example, let's say we're in some state and we have the following action values. We have 4 actions and these are the values. Now we have some target policy that might look like this and some behavior policy that might look like this. Now the specific values here and the shapes of these bars aren't super important as long as you trust that I did everything right and I'm telling you the truth. So given these two policies, your importance weights would look like this. And we have from the previous slide that the expected value of rho times q, if you sample actions according to mu, would give the expected value under pi. And we also have that the expected weight is still 1. Now, I'm going to do something weird here. Like, I'm going to modify these importance weights to look like this. So I'm going to rewind in case you missed it. I'm going to sort of increase the weight of the 4th action to be slightly higher, and then decrease the weight of the 2nd and 3rd action to be lower, and so that they're all equal over there. Now, I'm going to claim that the expected value of this modified rho times q is still the expected value of q under pi. And I'm also claiming that the expected value of this new importance weight is also 1. So assuming that this is true, we have these like different sets of importance weights that we can use to correct the distributions. But why might you prefer one over the other? So these are our 2 sets of importance weights that we have here, where in blue we have regular importance sampling, and in red, we have these modified importance weights. If you compute the variance of rho times q for importance sampling, we get around 0.96. And if we do the same thing for these modified weights, we get 0.25. So to summarize this example, there exist these alternate importance weights where weighting samples from mu still averages out to the correct expectation under pi, and these alternate weights can have lower variance than ordinary importance sampling. So the title of this talk was Value-Aware Importance Weights. Now, what do I mean by that? So we can go back to this example where we have regular importance sampling and these action values, and we know that this is true. Now, if I were to perturb Q and give you Q prime, we have that this is still true because those importance weights made no assumptions on what the values are. They don't depend on the values at all. But let's go back to the other set of weights. And I claim that this is true. But if I were to perturb Q and give you the same Q prime, this is no longer true. And so we have that these importance weights are now a function of the policies as well as the values. So if you wanted to correct this Q prime, you would need to compute a different set of weights that would work for this. So I've showed you this example of these value-aware importance weights, but where do they come from? How would you compute them? So we can cast this as a constraint optimization problem subject to the following constraints, where you've got the expected value of rho times q under mu to be the expected value of q under pi. And we also have a constraint where the expected importance weight is 1. Now, the second constraint might not seem as important because you can do off-policy corrections without this, but normally in reinforcement learning, we end up doing this long product of importance sampling ratios. And if this weight wasn't 1, we would get some arbitrary attenuation or amplification of your signal. And so given these constraints, if we have 2 or fewer actions, the only solution to these constraints is to do importance sampling. But if we have 3 or more actions, there are generally infinite solutions to this. And so a reasonable objective, given all of this mention of variance, is to explicitly minimize the variance of rho. And so we can set up this Lagrangian, where in blue we have the objective, which is the variance of rho under mu, and in red we have the 2 constraints. Now, if you were to take the gradient of this, set it to 0, solve for the Lagrange multipliers, and solve for rho, I'm going to skip the derivation, but it would give you this expression. Now, it looks a little intimidating. It's a lot more complicated than regular importance sampling. But before we move on, I'm going to refer to this specific instance of value-aware weights as sparrow. And so to try and make this a bit more digestible, we can split this up into 2 terms. We've got the blue term and the red term. If we look at the blue term, we've got the action value at time step t, and we subtract the expected action value under mu. So this is sort of like mean censoring that action value. And then if we look at the denominator, we've got the expected value of q squared minus the square of the expected value of q. And some of you might acknowledge that this is the variance of q under the behavior policy mu. And so this blue term is sort of mean censoring and dividing by the variance, which is sort of normalizing the action value. And now if we look at that red term, we've got the difference between 2 expected values, one under the target policy pi and one under the behavior policy mu. And so this is sort of like a measure of off-policiness. And so this makes it a bit more digestible, where we've got, you start with 1, then you normalize your action value, and then you scale it by how off-policy you are. This makes it easier to interpret, it makes it easier to remember, and sort of gives some hand-wavy intuition for why this might be doing what I'm claiming it's doing. And so to give some properties of this, of these importance weights, these are computed in closed form given mu, pi, and q for some state. And I'd like to emphasize that they're not learned or approximated even if these other quantities might be. And by construction, we have that the variance of sparrow is less than or equal to the variance of rho. And this is because importance sampling is in the space of solutions given by the constraints, and we are explicitly minimizing the variance. And in the on-policy case, we have that the sparrow weights are equal to 1 for all actions, and this is because that will satisfy the constraints while trivially minimizing the variance of rho. And an implication of this is that this still generalizes the on-policy learning in the same sense that importance sampling does. And another property is that if we sample this sparrow times q from the behavior policy, this provides an unbiased estimate of the target policy. But to clarify some potential confusion with this, it is still biased if q is trying to estimate something else and q is inaccurate, similar to how TD is biased. And the main implication of this property is that there's no additional bias by using these value-aware weights, at least for now. And another observation is that these sparrow weights can be negative. Now, I'm not really sure how to interpret what a negative importance weight means, but I'll note that it still has the correct expected value and has lower variance. And empirically, these sparrow weights tended to be all positive most of the time. They did end up negative sometimes, but most of the time they still remain positive. So to get some intuition for what type of variance reduction we might expect, I evaluated these on some randomly generated bandit instances where some behavior and target policy were generated as a softmax of Gaussian noise, and action values were generated as Gaussian noise but shifted to avoid any zero mean artifacts. And I specifically used beta equals 2 here. Now for these bandits, I swept over the number of actions ranging from 2 to 32,000, and I measured the variance of row Q and the variance of sparrow Q across 10,000 randomly generated bandits. And the results ended up looking like this. And so we can see that there is substantial reduction in variance when using these sparrow weights, but something that surprised me was that the variance was actually decreasing as the number of actions increased. At first I thought this was some artifact of how I was generating these problems, but we can see that importance sampling is going up as we would intuitively expect. And yeah, so another thing is that, what about clipped importance weights? This is something that's often done in the literature. For example, retrace and vtrace, and this is one way that people in the literature handle the variance of importance sampling at the cost of increased bias. And specifically, they would clip the importance weights to 1, and so I also tried clipping sparrow to be at most 1, and I call this re-sparrow. So if I were to measure the variance again, we can see that for both estimators, the variance substantially decreased. If you look at the y-axis, we can see that all of the variances are below 1, but the clipped sparrow estimator still had lower variance than the clipped importance sampling estimator. And I mentioned before that this introduces bias, so I also measured the bias of these estimators, and we can see that with the clipped importance sampling estimator, the bias is actually increasing with the number of actions, and again, surprisingly, the clipped sparrow estimator is decreasing its bias with the number of actions. And another way to measure this bias is to look at the magnitude of the importance weight, or the expected importance weight, because if this is smaller, it means that more of the importance weights are being clipped on average than normal. And so we can see that with the clipped importance sampling ratio in blue, the expected importance weight is decreasing as the number of actions increase. But again, the clipped sparrow estimator is increasing its expected weight with the number of actions. So this is suggesting that most of the weights are staying close to 1 and very little of it is being clipped, in contrast to the retrace. So yeah, we have all these really nice properties in the bandit setting, but there's a caveat to all of these results I showed so far. To compute these sparrow weights, it first requires computing the expected value of Q under pi. And yeah, it shows up in the expression over here. But this expected value is already the exact answer to this prediction problem. So you're first computing the solution, then using the solution to form the sample-based estimate to estimate the same thing. So it seems kind of redundant and maybe defeatist, but I'm arguing that the promise here is in the sequential decision-making setting, where you're trying to correct a sequence instead of just some immediate action. For example, you might have Monte Carlo returns, you might have multi-step TD, and specifically you're dealing with this long-term sum of rewards into the future, generated by a long sequence of actions. And so your values in this case would be the expected sum of rewards conditioned on some state in action, as opposed to just some immediate reward. And so if we're trying to learn these values, we need to form some estimate of this return under the target policy. And so we might start with something like this, where we've got a reward and a discounted future value. This is a one-step TD estimator. And we can see that this is an estimate of the return because because these values are defined to be the expected return from some point onwards. So it's a reward plus what we think will happen next. But these action values are sampled from the behavior policy, or that action value at time step t plus 1 is sampled using the action at time step t plus 1, which is drawn from the behavior policy. So we've got an importance weight to correct that action. Now, if we were to take this and then expand that action value to be another reward plus a discounted future value, and then simplify everything, and then expand it again, and then simplify everything, I'd like to point you to the structure that emerges here, where we've got this accumulating product of importance sampling ratios. And so we sort of derived per decision importance weighting for the sparrow estimator. And this shows that we could sensibly use this product of sparrow weights in a similar way that we do with importance sampling, even though the semantics of these importance weights might not be as clear what's going on when you take this product of them. But there is a caveat to this again, where if we go back to this one-step estimator, these importance weights are computed using the action values of time step t plus 1. And when we do this expansion, these weights are unaware of that sampled reward and future value. And so if those two orange terms are very different, that expansion doesn't properly replace Q, then this introduces bias into the off-policy correction of this estimator. We could avoid this if we use some trajectory-aware algorithm where you store the full trajectory and you can look forward to future samples, but we didn't consider that in this work where I just focused on the online incremental setting. And so because we're working with per decision importance sampling, a very natural candidate for this is TD lambda. So I extended a few algorithms to use these sparrow weights. Specifically, I used this Q lambda algorithm where it's defined to be a sum of expected stars to TD errors weighted by an eligibility trace with a decay rate of gamma lambda rho. Now there's many instances of Q lambda in the literature referring to different algorithms, but this is what I mean by Q lambda. And so if we take this algorithm and just swap in sparrow for rho, I'm going to call this algorithm sparrow lambda. And similarly, we have retrace, which looks similar to Q lambda, but we clip the importance weight in the trace decay rate. And resparrow would be retrace, where you swap rho with sparrow. So we have these 4 algorithms, and we're going to try and evaluate them. So I came up, yep, Abhishek. Yeah. Yeah, I'm just trusting the value estimates as if they're accurate, similar to how TD would. Yeah. Yep, so I first used this path world, which you can think of as a fully connected feed-forward neural network where you start on the left and you keep making decisions to move towards the right until you eventually terminate. And so the depth of the network represents how many decisions you have to make in an episode, and the width of the network represents how many actions there are. And specifically, I used 5 decisions, and I considered 8 actions as well as 32 actions. And I generated a different behavior and target policy for each independent run using the same procedure as the random bandits, but it was applied per state. And I swept over the step size and traced decay rate lambda and performed 30 runs per parameter combination. And Q lambda looked like this for 8 actions. And so for small lambda, it sort of works, but as you increase lambda, it struggles to manage the variance unless you use a really small step size here. But if we run sparrow lambda, it ends up looking like this, where it can tolerate larger trace decay rates. It generally has lower variance and can, I guess, handle it in general. Now, if we go to 32 actions, Q lambda barely functions. But sparrow lambda still can tolerate it and can tolerate larger lambdas beyond that. Now, if we were to use retrace, it ends up looking like this. And so we can see clipping does work really well. It does manage the variance. But if we look at resparrow, it ends up learning a bit faster, but we notice a little bit of instability for high alpha lambda pairs. But generally for reasonably tuned alphas or smaller alphas, it generally learned faster than retrace. Yep, and so after this, we looked at the Acrobot environment, where this let us look at off-policy control with function approximation, and we represented our action values as a 2 hidden layer fully connected network. We had a greedy target policy, and the behavior policy was epsilon greedy, where epsilon started with 1 and annealed to 0.1 over 25,000 steps. Now, something to note about the 4 algorithms I presented, once you reach the on-policy case, all 4 algorithms are exactly the same. And so when evaluating these algorithms, I only considered the first 25,000 steps because that's where there's a reasonable degree of off-policiness. And so I measured the area under the curve of the episodic returns and averaged this over 30 runs. And again, even though I'm using a neural network, this is still online with eligibility traces. And this is a depiction of Acrobot as a penguin rescue mission. So Q lambda looked like this in Acrobot, and Sparrow lambda looked like this. And so we can see that Sparrow did slightly better than Q lambda and had a bit lower variance. And point-wise, it generally did better for each parameter setting that you looked at. But retrace ended up looking like this, where it generally did better than both of those algorithms. And if we ran resparrow, if you properly tune it, they end up performing similarly within like statistical significance. But up is good. Yeah. Yeah, this is the area under the curve of the episodic returns. But when you use resparrow, we end up with generally flatter sensitivity curves. So this ended up being slightly easier to tune, at least in the direction of smaller step sizes. And so to summarize that, I proposed a general framework for these value-aware importance weights. I derived and analyzed a minimum variance instance of these weights. And then I extended some existing per-decision algorithms with these weights and empirically evaluated them. And some future directions for this, we could consider some other objectives. For example, non-negative constraints. We could consider the role of that second constraint of making the importance weight, the expected importance weight be 1. There's room for better theoretical analysis. Like, for example, we know that the true values is the fixed point of this multi-step operator, but it's unclear if this is a unique fixed point or if it's a contraction. And there's room for alternative multi-step extensions because I only considered this per decision extension to the multi-step setting and only the online case when you could do a bit better with a trajectory-aware algorithm. And yeah, are there any questions?
We have a mic for questions if anyone wants to ask something. I have one question in the meantime.
Yeah.
The difference between like the results in the Bandit case and the RL case are kind of different. Like you see like huge gains, especially at higher number of actions in the Bandit case. In the RL case, you didn't push the actions that high. In the path road, there's only up to like 32 actions. Do you imagine like one of the benefits of Sparrow is like its ability to handle larger action spaces?
I think that is a benefit. That's sort of the motivation behind Pathworld, where it let me systematically increase the number of actions. But after a certain point, it became hard to compute the true values to compare my results to.
Right. So 32 is, I guess, not as large as the number of actions you had in the Bandit setting. It went up to about like 10,000.
It went up to about like 32,000.
Okay.
Yeah.
What about continuous action spaces?
Yeah. So
infinite numbers of actions.
Like in this work, we didn't consider that, but if I had to consider it, I would discretize the space or keep track of some sample-based estimates of those relevant quantities in the expression.
Thanks. So in one of your slides, you had this thing about a trajectory-aware estimation. So how did your algorithm change? Do you have any ideas about that?
Yes. Where is it? Okay. Yeah, so normally, or at least with what my algorithm was doing, it was computing that weight using only the immediate action values. But if you had a full trajectory or you had the sampled information beyond that point, you could replace one of those action values with what actually happened and then compute the weights using that information. And so it no longer has the bias from the mismatch between Q and the expansion of R plus the expected future value.
Right. So in this case, the Sparrow coefficient, that doesn't change. It's just the estimate of the Q. That's the value that changes. Is that correct?
Well, changing the value of Q will change the Sparrow estimates because it is dependent on it.
Right.
Yeah.
Thanks.
I have one other question, actually. So when you did your experiments in, I think it was Pathworld, in calculating the Sparrow coefficients, were you using still the estimate of E pi Q?
Yes. Like it was learning Q, and then I was just calculating the current expected Q at each time step.
Do you have like any intuition on how much that bias, how problematic is that additional bias? Like if you were to use the exact E pi Q in the RL setting, would it make a big difference? I know it's cheating, but
I'm actually not sure if it would help because it's no longer a correct correction. Like it might be computing the expectation under some other policy and not the true, or not the target policy. Because in this case, like it's taking into account the behavior target policy and the current estimates to form an estimator for the current estimates. If you're using some other value function to compute the weights for your current estimates, that mismatch might end up increasing the bias.
Okay. Is it not my question?
There's a question from Shiva. He's asking, why do you want constraint to positive importance sampling ratios?
So initially I didn't want to, and I didn't, but when trying to analyze it theoretically or to say something about whether or not this might converge, the existence of these negative weights ends up making the key matrix no longer non-negative. And so there's no more bound on the spectral radius. It's really hard to make any statements about whether or not it's a contraction.
I guess if there are no other questions, okay. Yes, there's always one.
So would this make a difference, significant difference? We did, a really simple case like a grid roll. We got 4 actions, and we were doing something like Q learning. And I guess I want to ask also if it's only relevant for lambda, greater than 0.
Mm-hmm.
Okay, so we're doing Q lambda 0.9 in a grid world.
Mm-hmm.
Will this be a different algorithm that you think would be better?
I think so, and if I go past the end of this talk. Whoop. Okay. Yep, so I've got results in this little grid world for like a similar sweep over alpha and lambda. And I chose the best performing parameter setting and presented learning curves here. And so with tabular features, we still see that Sparrow and re-Sparrow end up generally being the best performing algorithms over Q lambda and retrace. And even with linear features, we see that retrace does better than Sparrow, but re-Sparrow still outperforms retrace there. And even if you do something like ETD, the algorithms all generally perform worse than their non-emphatic counterparts, but we see that the inclusion of Sparrow generally improved over the base algorithm that was using importance sampling. But with these ETD results specifically, I'm not sure that it's estimating what we are expecting it to estimate. It's not clear whether the expected emphasis is still the same under these weights, but the results seem to look positive.
So what's the increase in amount of computation per step with this Sparrow?
Yeah, so with Sparrow, you're computing 3 expectations. So it's on the same order as if you were to just run expected Sarsa, but not much more. Yeah.
We have time for maybe one last question.
So when you have a large number of states or actions, so I guess you did some experiments with the nonlinear setting. How are you computing the expectations? Are you taking, let's say, all the states in the cart poll and then pushing them through to get their values and then computing an expectation of it, or?
No, given a state, I would compute the action values for that state and just use that information only, just some array of action values for that one state. I'm not computing it for all states, just the current state. And then I would apply that importance ratio and then just forget about that information.
I see. Okay.
Yep.
Let's thank the speaker.